Hello, my name is Flora
Hello.
Huang, and I'm
My
from
name is
Philadelphia, USA.
Hello.
We are
Women in Data Science.
I became a WiDS ambassador because I dream of an equitable world where empowered women help humanity make better decisions through data science.
As a woman, I'm hoping more Peruvian women will be motivated to join this exciting field.
The WiDS community has really enhanced my sense of purpose in these life goals, and it has really built my confidence in such a meaningful way to be able to mentor, motivate, and support others.
The most rewarding and impactful aspect about my work as a clinical data scientist is to use the data generated by doctors, nurses, and the healthcare system to improve the care of future patients.
I'm delighted to bring this event to Pakistan, along with so many WiDS ambassadors worldwide, so that we can inspire all young girls or women to take up career in data science.
The use of data science to address climate change and sustainability issues continues to inspire me in my data science journey.
Through WiDS Alexandria, I've got the chance to meet with brilliant female professors, learn about the research, and bring that to my community as well.
I'm a WiDS ambassador because I wanted to inspire more young girls like me to join the field of data science. And I believe that in the future, there must be more women in this field.
I'm really excited to continue bringing WiDS events to my school and schools across Australia to empower girls to get involved in the field.
It's great that we've got women in data science events, and know that there's so many more inspiring stories as part of Women in Data Science journey.
Hi, I'm Carolyn Bertozzi, and I am a chemist who works in the area of drug discovery. I've had many opportunities in my life to collaborate with data scientists. They've been absolutely central to the work that we do. We couldn't have made the discoveries that we've made without having people to analyze very large data sets and to help us find hidden trends within them. Now, when I was growing up, I was somewhat insulated from the idea that women or girls couldn't be scientists because I came from a family of scientists. And when I was in college, I learned that not everyone had that privilege. I hope that all of you women data scientists or aspiring data scientists will truly feel that you belong in the field, because I believe it, and your participation is absolutely essential for us to bring the full benefits of data science to solve the big problems in humanity. So just as I was so fortunate to have a family that created an environment where I could believe in myself as a scientist, I'm hoping that you all have the confidence to pursue your dreams and that you help the generation that follows you in the same way that hopefully someone of my generation can be of help to you. Good luck with all of your work.
Microsoft just announced the death of every
Good morning, everyone. I'm Dipti. I'm WiDS Delhi Ambassador. I'm holding graduate degree in Information Science and postgraduate in Data Science from WiDS Pilani. I'm working with NatWest Group in Big Data domain. My area of interest in technology includes data science for social good and blockchain for transparency. And I'm hosting the WiDS Delhi event today. And I can't just tell you that how excited I am. On behalf of WiDS Delhi, I would like to welcome all the speakers, participants, and other guests present for gracing this event. I'm very excited to have you all here on WiDS Delhi Day-1 event. WiDS, Women in Data Science, is a global initiative by Stanford University that aims to educate and inspire data scientists worldwide. It also aims to support women working in the area of data science. In today's event, you'll get an opportunity to hear our amazing speakers who have been leading the way in data science. And when I say amazing, I really mean it. So we'll be starting our technical talk at 12:45 p.m. onwards. In addition, we have 3 rounds of data challenge, which will start soon. The first round of data challenge is quiz, where we'll be sharing the link on the platform where people who all have registered can attend that quiz. So I'll wait for another 4 minutes. After that, we'll start with the quiz. Thank you for joining, Pooja.
Thank you, Deepthi, for inviting me. Bye.
Yeah, so we have Pooja here. She's founder of uh, Julia INC. Yeah, so she's going to take you through the quiz round one. So she is going to brief about it. Yeah, over to you, Pooja.
Cool. Thank you so much, Deepthi. So hey everyone, this is Pooja, and we are like I'm the co-founder and CPO at Julia. I think I have not included it in my headline, so yeah, I would be correcting it sometime. Anyways, so regarding the quiz, which in collaboration with the WiDS and Julia, we are presenting to you. um, so about the quiz, there are going to be 30 questions. All of them are MCQ, that is multiple choice questions. And there is penalty for the negative for a wrong answer. So please be sure that whatever questions you are attending, you are 100% confident on it, like in it, like when we give those AI triple exam, those entrance exams, so like that, like those only, we have curated this quiz where you like for every positive answer you're gonna get +1, and for every negative answer or a wrong answer you're gonna get -1 as a penalty. Apart from that, there are two sections in the quiz. In the first section, the phase one, there are 30 questions, and each question consists of 1 mark each. 1 mark, that means 1 point. So phase one is of 30 marks. And then in the phase two, it is also a MCQ question, but the point and the weightage of the section is like 5 marks. So there is only one question which is analytical based, but the weightage of it is 5 marks. So please be sure that you are able to complete all these 31 questions in a span of 30 minutes, which is the time for the quiz. After 30 minutes, you won't be able to um, continue in the test. It will automatically get submit to us, and there is tracking as well, which gonna happen behind the quiz. So if you are opening any new tabs, if you are browsing anything else in your laptop or in your device, so it can be tracked. Although the information won't be given to you, but it would be with us. So please be sure that we are not doing any we are not using any wrong means to get ahead of the race. So that is these are the things from the quiz side. I hope I was able to make it clear. And the quiz will get start at 12:10 and will get finished by 50, 12:50 or something like this, so that if you even start after 5 minutes, you would be having room to get it extended. So yeah, that is the thing about it. And I think the links are live on the social media channel of for ours. I'm posting the links to them in in the chat section of this live stream as well. So please go over there, check out the recent post which we did, and you will find out the link to join the quiz. So for now it's 12:09 already. So, and because it's time driven, so I won't take much of your time over here. So bye bye guys, all the very best with this. And yes, let's see who wins the race, who are the top people. Bye everyone.
Thank you, Pooja, for the brief about the quiz. Yeah, so I hope it will be live within 1 minute, right?
Yep, that's right.
Okay, so wish you good luck to all. And once the quiz will get over, then we'll be starting with our technical talks. Yeah. and probably at around 1:30 or so, we'll be declaring the result of this quiz. We'll be announcing the winners. Yeah. Yeah, so we have extended the quiz timeline till 1 p.m. So now we are moving to the Tech Talk session. Please join me in welcoming our esteemed speaker, Pallavi Satsangi. She is going to share her expertise on federated learning in data science. Pallavi brings more than a decade of experience and expertise in retail, supply chain, payments, digital gaming, and banking domains as a project leader. Pallavi has done her engineering in computer science and holds a master's degree in business analytics. Currently, she is pursuing her PhD in machine learning from WiDS. She is currently working as a senior engagement manager with Quantify. As a part of her role, Pallavi is responsible for customer success and program management of AI/ML engagements. She has deep expertise in AI/ML, and her previous experiences include running large programs in driving delivery excellence and standardization across AI/ML engagements. She has been involved in developing ML solutions at scale and has guided project executions, managed the risk, quality, and delivery of projects. She has headed product teams and was responsible for product vision, planning, design, usability, and execution. So I welcome you, Pallavi.
Thanks. Thank you so much, Dipti, for the introduction. Shall I quickly present my screen?
Yes, please.
Okay. Please let me know once the screen is visible.
Sure. Yes, the screen is visible.
All right. Okay. Good afternoon, all. First of all, thanks, Deepti, for having me on this particular program. I think last year also I was part of this of your program, and it was quite well done and well coordinated. So it's again a pleasure being on this particular forum today. You have anyway given a detailed introduction about myself, so I'll just quickly cover again, maybe in a one or two liners. So hi all, I am Pallavi. I currently work as a senior engagement manager at Quantify, and I lead the entire AI/ML portfolio here at Quantify from a delivery standpoint. I have worked across different flavors of data science and machine learning use cases. Have been heavily involved in regression classification, forecasting, computer vision related projects. Um, as part of my thesis, I am working on federated learning with a flavor of computer vision and computational photography in it. And that's one of the main reasons why I thought, I would give a quick session on what FL or federated learning is all about, and how it can overcome a lot of limitations that traditional machine learning system has as of today. So that being said, let's just kick off. So we all know the traditional machine learning and how it works. It's basically your conventional approach where your data is at a centralized repository, and so is your model. So on the right side, if you can see, there's a quick diagram on how our usual machine learning models work, wherein you have different devices. It could be a laptop or a phone or say a vehicle, and all of them push their data towards a central repository. Now, this could be on cloud, this could be on prem or an edge device, so on and so forth. That's where the model is also trained, wherein it pulls in the data, all the consolidated data, trains the model, and then throws out the output. Now, that being said, what exactly, if things are going fine in the machine learning world, then what exactly is the need for a federated learning approach? Now, this is mainly because of certain limitations that our usual machine learning has. Now, of course, among the list of limitations that the traditional machine learning has, I have ordered it in the form of from the severity 1 to the nth level. The first and foremost being the data privacy issues. Now, when you're consolidating the entire data at one place, especially when you're dealing with like a sensitive data or a PII, right, personal identification information sort of a data, that being shared over the network is always a concern of privacy, as to it could lead to certain sort of breach that might happen, or some sort of an unauthorized access that can take place, so on and so forth. Now, the next part of as a limitation for our traditional machine learning is on the data transfer and the bandwidth. Usually, when we do our POCs, we have small Excel sheets or small CSV files, and sort of use that to train the model. But in real time, the data is pulled across various regions, various domains, various applications, and it's then stored at one normal, common data warehouse. And that transfer itself is a time-consuming process, and it's a very resource-intensive process as well. The third being on the compliance with regulations. Now, this is again one of a very important topic in terms of data science, data analytics, or machine learning, because we deal with a lot of data, right? So depending on which region you are, what sort of data you're using, what sort of a domain you bring in, there are a lot of restrictions and regulations around data. So imagine the amount of compliance and regulations that we have to sort of adhere to in our respective projects when you're pulling in data from different sources. So this is another limitations for our traditional machine learning. Moving ahead, there are the other ones. One is on data silos, right? You have the entire data in one place. That in turn makes it a little slow iterative process, because often you require repeated iterations when it comes to collecting the data, cleaning the data, or transferring the data to downstream, upstream applications, so on and so forth. Doing this is also leads to a certain lack of diversity in the data, because they're typically the data that is available is at the central location, and this limitation many times results in in the creation of the bias in the models that are going to be created. The next one is a single point of failure. We all know, you have it in one database or one data warehouse, and if that goes down, and if there's not replicated enough, and if that automation or the scheduling is not done well, you lose a good chunk of data. So this becomes another limitation when you come in terms of your traditional machine learning. So keeping all these limitations in mind, there is something called as a federated learning approach that has been designed. Now, what does this federated learning do? It is quite simple. It says that on the local devices, or we say them as client devices, the data is not pushed to a central repository. The data stays within the respective local devices. The model gets trained within the local devices itself, and it's just the weights that are sent across to the global model. Now, again, this global model, if you see on the right hand side, this aggregated ML model, it could be on your cloud or it could be on your prem, but that's sitting somewhere separately from all these local devices. Now, as part of federated, what it does is the model learns locally, bases the data that it has locally, and then it pushes the weights to the global model. The global model, then it takes all the weights from this clients, and then it aggregates the model. Now, there are different type of architecture that happens here in the form of how the ML model aggregates. Now, that depends upon our use cases, the type of data that we are using, what sort of problem statement we are solving, and so on and so forth. Now, once the model takes in all these weights, it again retunes the model, the global model, retunes it to a certain till that point of time wherein there is a good amount of accuracy that is observed. So once the global model is able to create that final version of the model, it then pushes back the respective model to the local devices. Then the local devices, again, it's like an iterative process. The local devices again take in the model, and they sort of, again, if they have some new data that has added to their devices, they start retraining the model, and so on and so forth. So what federated learning is doing is, instead of making everything central, it has made it in a very decentralized approach. So that is one of the major advantages of bringing in this particular concept. Now, coming to the core concept of federated, it involves a collaborative process between the central server, like how I had showed the figure before, and the respective client devices. And typically, this is how it works. The first step is on initialization, wherein you have the central server that initializes the global model by defining whatever respective architecture that it has, and that becomes your starting point. After which, the global model is actually distributed to the client devices, the devices that are going to participate into the federating learning process. And they receive a copy of your global model, basis which your local training kicks in, wherein now the local devices take in that particular model, takes in its data, and starts training, or rather retraining themselves that particular model again. After the model training is done, a model update happens, wherein your entire model parameters are sent back to the central server. It's not the data, it's not the entire model, it's nothing that is shared except for the weights that we pass across the network. Post which, the central server, it does an aggregation and restarts retraining again. Once the retraining happens, the model gets updated, and that's how, like I mentioned, it becomes like an iterative process. Once the model is ready, it pushes back again. The retraining happens with the local devices, and they send back the parameters back onto the central server again. So this is the entire structure of how the federated works. If you can see the figure here, just seeing if okay, it's happening. All right. So if you can see the figure here, we have a lot of local devices, and say our auto completion. Thank you for the, and it's a blank. Now this is one of the classic examples that we use across for federated learning, wherein when you type your messages and all, or the next recommendation of the text message that has to come, that happens via a federated approach itself. And federated learning is a concept that has come from Google. So we know how well it works for us. Our search and all of that works very well. The Google search and our mobile searches, they work quite well. And the idea behind them is your decentralized approach of the model training that happens. Federated learning as such has a lot of advantages, but whenever we talk about federated learning, it's the data privacy that comes as one of the key advantages. Now, how does that data privacy happens is because now the data is stored locally and not centralized, right? So all our governing and all of this issues that we were seeing has drastically reduced the minute you go into your FL approach. Second thing is your data movement is also reduced, because now your data resides in your local devices, right? So all the data transfer, the network bandwidth, and all of that is also minimized. Third thing is, even though you have your local data within the local devices, but still there are certain aspects, certain weights and all that are being shifted onto the network. We also have privacy preserving techniques in federated learning to ensure there is no such sort of a privacy mishap that happens actually. So there are certain techniques that are taken care of in federated. Along with that, we discussed on local model training. So overall, it's the limited information exchange that is happening when this entire process of model training, retraining, pushing, aggregation happens. It's a very limited information exchange that happens. So now, that being said, where all do we use federated learning, right? What are the in a broader level, what are the applications of federated? Now, when we talk about sensitive data or managing about data privacy and things like that, the first scenarios that comes into our mind is on healthcare. So obviously, there's a lot of healthcare information which is very personal. There's a lot of patient-related information that is quite private, and that is something that you cannot share it openly across the network. So that being said, healthcare is one of the primary places where federated learning techniques are used. Post which you see in financial services, anything with respect to finance, their PII related stuffs. All of this is quite a sensitive information. So in financial services also, we use a lot of federated approach, Then we have our autonomous car. This is again a huge thing in the manufacturing domain right now, wherein every vehicle, or rather every car, would be learning from its local data that's being generated, basis which there are a lot of things that can, a lot of use cases that generate out of it. It could be like a maintenance of the car, or predicting when a component can fail. So we have a ton of use cases that can come out for autonomous vehicles using the federated approach. The next one is on the smart cities. Of course, when we are moving towards the direction of smart cities, smart factories, and so on and so forth, and that's nothing but in the end, there are a lot of sensors that are going to be placed, and we know when you install sensors, the amount of data that gets generated. Now, do we really want to push all that extent of data to one location, which is coming from different sensors, or sort of break it out, decentralize it, and ensure that the data, huge data, is there locally, and it's also being used to train the models. Similar way, I like how I explained about smart cities. I think the subset version of it would be the Internet of Things, which is the sensor-based applications, and the major uses here are predictive maintenance, anomaly detection, and environmental monitoring. We also use predominantly in NLP. One of the examples that I showed was on the text, right? The thank you for the next word prediction, which is feedback. NLP, or the text data, when it is huge, decentralize it and ensure that we take a federated approach for it. Mobile keyword prediction is another, and the voice recognition is another such area of application. We have a lot of it. We have smart farming, we have edge assisted object detection, so on and so forth. So these are the broad domain areas where we use our federated learning. It's nothing but a lot of data being generated. It could be a sensitive data. We do not want to push it across the network. So we use an FL approach to solve our problem statement, so that we are able to use the machine learning advantages while ensuring that the data privacy is mentioned. And when we talk about federated, we say there's a client, there's a server, and there's an aggregation that happens and all. But there are a lot of different architectures that are in place when it comes to how you want to implement your entire architecture. It basically falls in one of the four broader areas. First is the client management patterns. Second is called as a model management. Third being the model training patterns. And the fourth one is the model aggregation patterns. Now, this is like a broad level. Under each of this, you might have a number of patterns. I will just give a quick snapshot on the type of patterns that we have, and just take about few of them and give a quick explanation as to how this architectures actually make sense for us. So when we talk about client management patterns, we have a client registry, a client selector, and a client cluster. When it comes to model management patterns, we have predominantly four again, which is on the message compressor, model replacement trigger, model co-versioning registry, and the deployment selector. When you go to the third one, which is the model training patterns, you have a multitask model trainer, a heterogeneous data handler, and an incentive registry. So on for model aggregation patterns, different ways of how we can aggregate it. It could be in the form of asynchronized, it could be decentralized, it could be hierarchical, or it could be via a secure aggregator. I will quickly move on to few of the patterns and how in your federated approach, the selection of client and the model making decisions are actually made, the architecture revolving around that. If you see here on the right hand side, we have a central server, and as an example here, we have three clients. Now, there is something called as a client selector, wherein this is something that is placed on the server side, and the server gets a vote to choose which client it wants to participate in the federated and which client it does not. So here, if you say that it has a registry which it maintains, saying that, okay, I want to work with this particular client and the third client, but I want to exclude this client. There could be various reasons. Maybe that excluded client is not willing to participate in the federated approach, or they do not have that amount of data, or they do not have a legit data which the server is actually looking for its model creation. So this is one of a good approaches when it comes to your architecture wise. And what are the benefits that we receive out of this particular architecture is mainly in terms of its resource optimization, system performance, and the model improvement, model performance rather. Moving on to the next, a similar sort of an architecture is called as a client cluster pattern. Now, as the name suggests, there's a cluster of the devices for the client that is made, and this is again maintained by the server. Now, why does the server need to do it, right? Say, for example, a cluster of a client which has taken, say, ABC clients have, and it's trying to perform a classification task. Now, client ABC might have images which are pertaining a lot, taking dogs, while the second cluster, say the client XYZ, it also has images, it also wants to do classification, but say more than dogs, it has more number of images of cats. So what the client does is, instead of treating them as separate, it tries to create a cluster of them, and when it is trying to share the model, it shares one model to the this particular cluster A and another model to cluster B. Similarly, when the weights are being sent to the client here, if you see, the cluster of A sends it one sort of a weights, while the cluster B together sends one set of weights to the server. So this is another approach of your another architectural pattern for federated. Now, the third one being a model replacement. Now here, if we see, assume there are 4 client devices that are participating in your federated. That means they're in constant touch with the server. And say the 4th device, you observe there's a immediate degrade in the performance of the model. So it can sort of, have a connect with the server, and the server will deploy a newer model to this particular client, while the other client devices works as it is, because maybe their performance is not degraded to a drastic level. This is another sort of a pattern. The fourth one, when we call it, is the same thing. It's a deployment selector. When the server, it has various copies of its same model, and it deploys to that cluster of clients that it wishes to. Again, depending on the use case in the scenario and the pain point that we are trying to solve here. The last being, there are times when, say, the client does not want to participate in the federated approach, right? Because maybe it's a mobile phone owner and he does not want to sort of participate in this entire process. So there's something called as an incentive mechanism, wherein we monetize the clients if they are willing to be part of this federated approach, like trying to solve any of the particular pain point for your respective project. So this is another sort of a pattern that is used when it comes to federated approach. Moving on, we saw about the different applications and the application areas where we can use the federated learning. That being said, let's take a real-time example of how the entire line by line or the step-by-step process for the federated is done. And we will take an example of your medical image analysis. Say there is a consortium of hospitals, and there are a lot of patients who come in who have got lung cancer, and this is more in terms of to detect whether the patient has got lung cancer or not. Now that is my problem statement. We know we are going to use image analysis, image analytics, or apply classification onto it and find out whether that particular patient has lung cancer or not, basis the past history of the images data that we have. Now, why does federated becomes important here is again for two. Say in my local, say about in 100 kilometers, say I have about 20 hospitals. In that 20 hospitals, there are a lot of patients who walk in who have this lung cancer concern. Now I do not have to take all these images and push it to one place. Second thing, maybe while I'm trying to push all this data, this is sensitive data, there are a lot of privacy concerns around this patient's data, and I would not like to move it across the network. So this becomes a very good classic example for us to implement a federated approach. So here, if you see, we have these boxes are nothing but local data when we're saying they are hospitals, and how all these hospitals are doing their own model training, and all the local updates are being sent to the central server, basis which your central server again gives you back, it retrains and gives you back a better version of the model, which will be able to better classify as to whether the patient has lung cancer or he does not have lung cancer. This is a similar, a little more in depth that I have just put in here as to how the hospital's local servers are, how local databases are, and how the model updates, aggregation, and all happens. If we go in a very machine learning technique, the first would be our data preparation step, right? Wherein each institution or rather each hospital, it's going to collect its image data related to the lung cancer. It could be scans, x-rays, any prescriptions, so on and so forth. And their data is pre-processed, take out all its sensitive information, things, all of that, and whatever analysis, feature analysis needs to be done, whatever data transformation needs to be done, all of that is done on your data. Once that is done, it becomes, the next step comes to your model initialization. Say here, for example, you're taking a CNN model. So now your central server has a CNN model, and it pushes that basically that model to your local systems. And then your local training triggers. Now each hospital, it'll train. When I say hospital, I mean the your basically your systems that are present there at your hospitals, and they train and they share the model using the local data, and then the training happens independently at each of this particular local devices. Once that is done, then the local weights are sent back to the server where the model aggregation happens. And the next one is again the model updating, wherein the aggregated model is then sent back to the participating institutions and their local models are replaced with this new model. Then the institutions, they update their models using the aggregated parameters received from the central server. Now, once this is done, ideally it ends here. If you're doing some sort of a classification, we check how our precision is or our accuracy is, or our recall is, and if we are really satisfied, we start using that model at each of our respective hospitals and sort of classify whether the patients have the lung cancer or they do not have the lung cancer. That's where your validation and evaluation comes in. And throughout, of course, while we are doing this entire process, we are going to ensure that the privacy and the security measures, they are implemented, all the security protocols are in place, all the encryption, decryption, whatever logic is there, that has been implemented correctly, and to maintain absolute data confidentiality. Along with this, the last would be your collaboration and your knowledge exchange, which is the participating institutions. They can collaborate among themselves and they can exchange the insights. Again, what sort of experience they found or what sort of techniques they have used to collectively improve the model performance. So this becomes one of your real case use case that uses heavily your federated learning approach. Now, moving on, what are the frameworks that we use, right, for your federated learning? Now, we have all these big organizations, they have their own inbuilt federated learning approach. Like you have IBM, you have Microsoft, you have Google. They all have their own suite of tools to perform the federated learning. But that being said, I will cover the top 3 open source ones, the ones that at least I have worked on as part of my thesis. Which works well. First one being the PySift. It's a simple Python library which is built on top of PyTorch, and this gives you the notion of, or rather a simulation. It creates that simulation of your client and server, a multi-node system basically, wherein you can define saying that node 1, node 2 are your clients and your node 3 is your server. So it gives you that sort of a simulation. So it becomes very easy for us to take in whatever code or whatever use case you're trying to solve, right? Forecasting, it could be classification or regression, and how are you going to put it across in your federated approach. The second is TensorFlow Federated. This is again open source framework which is developed by Google. This is also quite good. PySift and TensorFlow, and the third one that I'm saying, they're very easy to install as well, as long as you keep in mind about the versioning between your Python framework and your Conda. You should be sorted. They are quick to get installed and get to start working with. TensorFlow is again another one wherein you can simulate the entire federated quite well. The third one is called as Flower, which means federated learning of weighted aggregated models. This is again an open source federated, which is being developed by University of Oxford, and it gives you this high level APIs for federated learning, and it allows the users to define what sort of tasks that you want to perform and how many devices you want to sort of distribute. Again, the whole simulation process works very well on Flower as well. So these are the top 3 frameworks that are predominantly used if somebody wants to get into the federated part of it, learn and do some hands-on as to how that entire, architecture and the mechanism works. Now, moving on, we spoke about data privacy. So obviously, there will be a lot of security protocols and encryption techniques that needs to be implemented as part of your project execution, or rather your use case execution. I will cover few of the very key known ones, and the very famous ones, at least the ones that are predominantly used in your use cases. The first being your secure aggregation, which is nothing but your aggregation of model updates. It's performed using quite secure protocols, such as you have MPC here, multi-party computation, and basically this is to prevent any participants from learning individual contributions. So the local device A should not be able to know what the local device B is sharing across. So that sort of privacy is what is given by secure aggregation. The next one is on differential privacy. It is basically what we do is there are times when I'm sending weights. I do not want to directly expose them over the network. What I would like to do is I'll add in some more noise to it, just so any sort of sensitivity that is there in my data that I'm being sent is sort of distracted by the noise that I'm adding to the data. So this is one level, one form of a security protocol that we can implement. Similarly, you have secure parameter transmissions. Again, encryption techniques when we are trying to transport basically the model parameters and any updates that are happening between the devices. Similarly, you have secure initializations, which are cryptographic techniques basically, which are used to secure and initialize your global model updates at your central server. And then when it is being distributed to the participating devices, this is where your secure initialization comes into picture. Similarly, you have a secure model evaluation and a federated authentication. Also, you have something as secure device verification and secure data transformation techniques. These are again, more or less all of them are towards maintaining that integrity and that authenticity of the entire process between your participating devices and your server. Now, that being said, everything looks very, hunky-dory in trying to implement federated, right? But there definitely would be some challenges and some limitations at this point of time while we are trying to work towards a decentralized approach. Now, what all could be the limitations or challenges, right? The first one being that federated learning, it requires frequent communication, like we know, right? Say I have a phone and I have an app which is basically trying to classify a lot of images, different type of images. It could be a multi-classification problem. Now that means my local device, that is my phone, needs to be connected with the central server. So this leads to a communication overhead, obviously, because there's going to be a lot of frequent communications that's going to happen. Similarly, there's going to be a heterogeneous device, right? Heterogeneous in terms of the devices, like my phone, as an example, could have a completely different storage capacity, a different computational power, a different network connectivity. And while the other phone could be maybe have even a better computational power, a better storage capacity, right? So the local training that happens also depends upon the type of the client, how the client devices or what the client devices rather are made of. So this is another sort of a limitation when it comes to federated. Similarly is the data heterogeneity, wherein the data that is collected from the different devices, it could be of different distributions. This could also make it very harder to train a model and train a model which will actually perform well after, of course, repeated aggregations and repeated iterations. It still could make it very difficult for the model to train and bring it to that desired state, wherein it could give us the sort of accuracy that we are looking for. And when we talk about federated, the word that comes is decentralized. That means there's definitely a lack of centralized control that happens here, because the central server, it has just very minimal control over the training process that is taking part locally in the local devices. Add on to that, we have something called as a non-IID data, because the data comes from different devices. They're all independent. And but in real scenarios, when you see that the devices may not have the same unique data distribution, right, leading to a non-ID data challenges. While we say that what that can also do as an extension is introduce that sort of a model bias, because due to the variations that we have in the device populations and the way the data is distributed, the models that have been, or rather the federated models, they can sort of exhibit bias, and which might, affect disproportionately for certain group of devices. Like I said, say for example, there are certain clients who are participating from a certain region, while there are another set of clients who are participating from a different region. Now, for that region, the sort of images that they have collected is quite different to what that is being collected, say, from the folks who are present in region A. Now, the model gets trained on this data, while the model also gets trained on that set of data locally. So this becomes very hard. Say if the region B has lot number of clients when compared to region A, definitely the sort of data that on what it is being trained, and the sort of weights that are going to get generated out of it, which are going to be pushed to the central server, will definitely induce some sort of a model bias. So one of the things that we can do here is to ensure, the regions that you're picking, or the participating devices that are picking up for as part of federated approach, we have to keep in mind the sort of data that that it is being trained on, the weights, out of the weights that it is generating, and end of the day, how it is impacting the model while it is aggregating and it is retraining. Similarly, scalability becomes an issue, because imagine a huge number of devices are coordinating. There's a lot of to and fro communication that's going to happen. How are we planning to scale this entire approach up? Say if my entire participating crowd just doubles or triples very frequently. So scalability is one approach that we have to keep in mind while we are working on federated. Second, the next would be the lack of global knowledge, obviously, because each device, it has access only through its local data, which means that the global knowledge of that entire data set is not available during training. This basically limits to a certain extent, not always, but to a certain extent, it does limit the model performance. The next is on the system heterogeneity, wherein the devices that are participating in the federated learning, they, again, similar to it, they run on different operating systems, they have different hardware configurations, they use different programming languages, they might be compatible for certain data, they might not be compatible for other data. That standardization is something that is not there across the entire client devices or the participating devices. So this becomes another sort of a limitation when it comes to federated learning. Now, what is the potential advancement that we foresee, right, or in the future research areas which involves federated? Now, there is something called as federated learning transfer, which is nothing but there are techniques that can be explored to leverage the knowledge gained from one federated learning task and apply it to an another related FL task. Another use case that we can think of is adaptive federated optimization, wherein what happens is the federated learning optimization techniques, it can dynamically adjust the learning rates, how it's going to tweak the model parameters, how it's going to tweak the model architectures based on the characteristics of the individual devices, or based on the way the data is distributed. This can help in leading to the improved basically the convergence of the model, and the generalization of the model will be much better. Similarly, we have something called as, we know of reinforcement learning. Similarly, an extended version to it becomes your federated reinforcement learning, which is wherein you create, or rather you design algorithms which basically allow multiple devices to collaboratively learn. So imagine there are two different FL systems or FL environments which can collaborate and learn from each other. That's like an extended learning from what we get out of RL, out of the reinforcement learning. The next to it is the federated meta learning, which is mostly in terms of federated learning to enable devices to learn, that is to quickly adapt and to change its model or specialize its model to ensure the model behaves in a much accurate form, and the model is more in a more generalized form, while it also is maintaining its all the security and its data privacy and the data locality. All these aspects are also taken into consideration. So this is another area of focus in future that can happen when you combine federated with meta learning. What are the sort of future AI, what's the sort of impact that federated learning has on the future AI and machine learning is, until now we used to have a centralized approach. With federated, we can think about a complete decentralized AI application format, especially with a lot of use cases being seen around edge, a lot of use cases around IoT, your real-time analytics, your decision making, without, and you can do all of this without relying on a central server. Second is what we can also see an impact would be on the data sovereignty, right? Because here it empowers the individuals, the organizations, basically the organizations, the companies and all, to retain control over their data while also contributing to the model training. And this is one of the key concepts of data sovereignty, which to a larger extent federated learning is able to adhere to. The next is on the democratizing the AI. We all know that it now with FL, which is with a decentralized approach, it will help us allow organizations which have that limited resources to participate in the model training, right? And that will help them level their playing field, and also sort of involve in in their machine learning use cases, which directly would help them solve their pain points in their area of work. Collaborative model development, definitely, your decentralized approach from federated that we get, it really helps in in collaboration among various organizations or institutions for further model development and improve generalization, because you are training models on diverse data sets from various sources. Federated learning helps to improve the generalization of the model, right? So all that overfitting things and all that we talk about, because it does not has that variety of the data. From the federated learning, to a certain extent, this can be taken care of, because you have a large amount of diverse data spread across, and the local training of those on those data are also happening. Next is on edge. Like we said, that there are a lot of applications that are centered right now on edge, and on IoT. So a lot of good aspects of federated can be applied here on the edge devices, because it helps enable the edge intelligence and the real-time decision making. Similarly, we have a lot on resource efficiency, because everything is taken care of locally. So your central repository or the central server or your entire central environment that you have can be made in a much more resource efficient way. And the next is on the compliance that we already discussed on, because a lot of compliance issues can be solved when federated comes into picture. So I think I'll just like to conclude saying that these are just basics rather of that I've covered today on federated. We have just covered on what actually is the need for federated, what's the concept that is running behind the federated, right? How federated learning helps with data privacy. What are the broad range of applications that are employed when it comes to federated learning, different architectural patterns. We went through one real-time example of how the entire process from start to end happens. We glanced over a few of the open source frameworks, which are quite easy to use and adapt to when you are trying to create your own federated learning use cases. We also covered on a quick level on the security protocols that are present, and the encryption protocols that are available. And we went through the challenges and limitations of federated learning, and what is the potential achievement or the scope of work, or how the future use cases look like for us in the near future when we go with this entire decentralized privacy enhancing mechanism. So I think that's the end of my session. You guys can feel free to reach out to me on my email ID, and I'm quite active on LinkedIn, so you can always connect with me over LinkedIn as well. So yeah, thank you so much. Dipti, you're there?
Yeah, Pallavi, I'm here. Pallavi, we have few questions.
Sure.
So I'll read it out for you. So the first
Okay.
question is, in the federated learning, how do we protect the denial of quality of model? Let's say bad devices in the network and participate in federated learning. How do we ensure it would not impact global model quality?
Okay, so this is one that I was talking about, the architectural pattern, wherein when the server is able to notice that there is certain weights from certain clients that are coming in, which is leading to a degradation of the model performance, it can choose to exclude that particular client from the from participating in the federated learning. So that's where that was the client selector pattern. The server basically has an entire registry of the participating devices, and it has the control on whom to select, on whom to unselect from the participation. So that's how it can ensure that the model degradation does not happen.
Okay, and a part of this, there is other question as well. What would be reaction time of the global model if things change very fast at the edge device level? That is, how fast it can react to the situation in the network and adapts global model.
This depends again on your configuration and on the use case that you're trying to solve. When you are having that connect between the client and the server, now you have your configuration set in place as to between what time you want to send the updates and the global training to happen. Now, if your training, usually global training is like it's something like a complex use case that you're trying to solve. So definitely it would take a while for the global model to retrain and to push over the updated model. But that being said, on edge devices, it is quite fast because they all more or less try to remain on the same network. With the cloud, there could be certain latency, but that is something that can be worked upon and tweaked when you are trying to have that entire, machine learning ops in place. You can try to tweak up and improve the latency part of it.
Okay, and the next question is there from Atul. Yeah, how local, that is, how local devices will update the model. Do they need to train locally? If so, how they adapt the model that was trained on global server? Is it partial fit? Then what about the tiny ML models and ecosystem?
Yes, they retain on those models, but the first model comes from the central server, which is pushed to the local devices. Now the local devices have a model, they take in the new data that they have, or if they have not been trained at all, they start with their data that is there, and then adjust the weights to see what sort of accuracy that it is coming. Basis that, and basis the configurations that has been put between the both the parties, the model, the weight push happens from there on again. Oh, I think I can see the question right now, his question on the screen.
Yeah.
They have to train the model locally. If so, how they adapt the model that was trained with a global server? See, when basically you have a set of methods, around 3 to 4 methods that the client needs to follow. One, a method which tells you how the model training is going to happen. You have another method which gives what is the accuracy or whatever is your success metric, right, that has been defined, basis which it can take a call, the model basis the comparison, it can take a call whether it wants to push back the updated weights, or whether it wants to wait some more, take in some more data and keep training locally. So yes, the training happens, it happens at the back end. I hope I was able to answer his question.
Yeah, I don't think Any other question we have? Yeah. So if at all, guys, do you have any other question? Pallavi's details are there right on the screen. You can reach out to her for details about federated learning. Yeah.
All right.
Yeah.
Yeah. Thank you so much, Deepti. Yeah.
Yeah, so on behalf of WITS Delhi, I want to express my sincere gratitude to Pallavi Satsangi for her valuable contribution today. We are truly impressed by Pallavi's captivating delivery and her ability to make complex concepts accessible and relatable. We hope to have the opportunity to work with uh, Pallavi again in the future and invite her to share her insights at upcoming events. Once again, we extend our heartfelt thanks to Pallavi for her time, expertise, and for her engaging presentation. Thank you so much, Pallavi, for
Thank
joining
you
us
so
today.
much. Yeah.
Thank you
Thank
for
you
your
so
time.
much for having me. Thank you so much. Yeah. Take care. Bye.
Yeah, thank you. Bye bye.
Bye.
Take care. Yeah, bye. Okay, so now it's time to announce the winners of quiz round one. So I would like to invite Pooja for the same. Welcome back, Pooja.
Okay,
Pooja, you are on mute. Yeah.
yeah. Okay, cool. Thank you, Deepti, for the things. So guys, yeah, there were like a lot of people who who give this round one, and we have shortlisted 28 students from all of the responses we got. But and the fun fact is that out of all these students there is only one team who was able to solve the question which was there in part 2. So kudos to that team. I'm going to send them a separate mail who were able to solve it right. uh, because I think most of you guys got confused with the option B, which which like in the first go we thought that 0.32 is the correct answer, which is not. The answer is 0.42. I'm going to send the question again because it's kind of analytical question which which you should keep on solving if you want to go into the AI field as a domain expert. Okay, all right. So regarding the students who got shortlisted, those 28 names. So because it was very difficult to map the names with the email addresses, what I did is I masked the email address of all of you guys and presented them as the username. All of you who are shortlisted must have received an email on their registered email ID. Although to make sure that we are not lacking anywhere, I'm gonna send this on our YouTube chat as well. So I'm pasting the username here in the chat. Deepthi, could you please copy that and send it on the YouTube chat?
Yeah, sure.
Yeah, so here we go. So these are the username, guys, because I didn't had anything to map it with your like first name or last name. So I used the username of your email addresses to let you know who got shortlisted. Also, we have also sent the emails on your on these email addresses itself. So please make sure that you check your emails, as well as please check your spam, because sometimes it falls into spam folder into the spam folder as well. So yeah, that's it. So congratulations to all these 28 teams.
Yeah, so I have
And
already shared the
perfect.
names in the chat box. So
Yeah.
congratulations to all the winners who
No,
all are
not the
moving
winner.
to round two.
Yeah,
For
yeah,
round two.
yeah, yeah.
Yeah.
Yep. So for round two, and so for round two, we would be communicating what exactly it is, what you need to do in particular for the round two. It's gonna be more engaging. It's gonna be more fun. So we would be sharing with you the details for round two in our tech talk, which is there at around 2:30, right, Deepti?
Yeah, that's right.
Cool. So at the at the end of it, like at around 2:50 or something, we're gonna share with you the details of the round two, what is there and what you need to do to move to the round three, because there are 28 teams. So for round three, we're gonna select 5 teams, and yeah, and then they would be competing against each other tomorrow in a presentation round. So yeah, that is it from my side. If you have any questions related to quiz or anything, please shoot me out your questions or feedback or whatever at pooja@dulaya.io, which is my email address. So yeah, that is it, Deepti, from my side.
Yeah, thank you, Pooja, for pitching in and announcing the winners. Yeah, so um, we are good to close right now, right? So let's catch up again after lunch at 2:30, wherein we'll be starting with the tech talks, and after that we'll be discussing that what are all the things we are going to do as part of our round two. Yeah. So till then, thank you so much for joining us, and we'll see you at 2:30. Thank you.
Yeah.
Bye bye.
Thank you.
Thank you, Pooja. Bye.
Thank you. Thank you, Deepti. Bye.